Okay, so let us start the continuation of the previous video, and here we will start with the last expression that we talked about, and that is this. So here we are trying to maximize the number of microstate to represent the thermal equilibrium of that composite system of our interest, and once we try to maximize this gamma, that means del gamma should be equals to 0, and also the fact that it is an isolated system, that composite isolated system, so this relationship is true, and if we substitute that, we come to this kind of expression. That means we take one side, we take the one term in the right hand side, and then we divide by gamma 1 and gamma 2 product, and then we come to this, and then this can be rewritten as this, okay, because 1 by gamma del E1 should be replaced by dl n gamma 1. Okay, so only thing is n1 v1 as a subscript, that means these numbers are constant, so you should put it here also. That is a typographic error, so please include that. So given this, what we find is that this term is completely a term associated with subsystem 1, and this is the term associated with subsystem 2. So the property of subsystem 1 is equal to subsystem 2 at thermal equilibrium, because this is the equilibrium condition at which gamma is maximum, and that condition brings us to this relationship. And then we realize that actually there is a property, therefore there is a property which says that two subsystems are same at thermal equilibrium, that property. And we know what there is a property which remains same under thermal equilibrium, and that is from 0th law we know that is temperature, right? So these terms must be related with temperature in some sense. Now if we multiply that Boltzmann constant K in both sides, then KLN gamma is entropy, so this can be written as del S1 by del E1 and del S2 by del E2, and that term if we define as 1 by T, that means 1 by T equals to del S by del E at constant number of particles and constant volume. This gives in a way the definition of the microscopic definition. Why? Because S is related with microscopic information, that is the number of microstates. So this is the connection through which we are defining now the thermodynamic absolute temperature as del S E by del E at constant NV is equals to 1 by T, where T is that absolute temperature associated with the system. So this is actually the statistical mechanical definition of temperature that we started. This was the goal for us to find out this relationship, and that is the statistical mechanical definition of temperature. And we then see that what happens, what it tells is that if we have a plot of entropy versus internal energy of a system, and then the slope of the curve of S versus E, that will be related with 1 by T. And if this term is positive, which is most of the cases it is true, that with increase of internal energy system's entropy increases, that means the slope is positive, then your temperature of the system cannot be negative. Temperature always has to be positive. However, the question is, can there be some condition under which this can be negative? That means with increase of internal energy, system's entropy decreases, then this will be negative, and under such condition temperature of the system, absolute temperature of the system, can be negative. Remember, it cannot be 0, right? Thermodynamics third law says unattainability of 0 degree Kelvin temperature. So that temperature cannot be 0. However, can it be negative? That is the question. We will discuss those things in our following videos later. Also, one thing, just last final thing that you should remember is that this is the relationship, one of the relationship of Maxwell's relation. So that is the small purpose of these two slides, through which we try to establish the relationship or the definition of thermodynamic temperature from the statistical mechanical point of view. So let me stop here.